This is an air position indicator. It was used in the latter part of World War II, primarily in B-29s in the Pacific, and later in the post-war years. It was designed to be used with the Fluxgate compass system to tell the navigator his latitude and longitude. To do its calculations, the air position indicator needed two pieces of information. It needed to know airspeed and it needed to know heading. The whole system was comprised of four components. There was the airspeed indicator, a controller, a pump, and an amplifier. Of those four components, I only have the air position indicator. The controller worked with the pump. Inside the controller were two diaphragms that were connected to each other with a switch in between. One diaphragm was actuated by pitot air pressure, and the other diaphragm was actuated by the pump, which was run by the controller. As the pitot air pressure pushed its diaphragm in one direction, activating the switch, the pump then came on and pushed air back against the opposite diaphragm, trying to neutralize the switch. During this process, as the pump rotor turned, it turned a rotary drive shaft which fit into the back of the air position indicator. That rotary drive shaft then gave the air position indicator its mileage information. In the original models of the air position indicator, that same rotary drive force actuated a ratchet and pawl system, which in turn worked these gears to turn the heading needle. And the ratchet and pawl system was turned left or right using this solenoid here. The amplifier took signals from the Fluxgate compass repeater indicator, which was a Magnuson, and then converted that into a signal that would run an autoson in the air position indicator. The autoson is located here. The autoson signal would then go back to the amplifier and be rectified into DC. And when the stator was moving counterclockwise or clockwise, that DC signal energized one side or the other of this relay, which then allowed the ratchet and pawl system being driven by the rotary drive shaft to turn the heading needle. There was a latitude and longitude side. This is the latitude side, and depending on which direction the heading needle was pointed, determined the position of two racks that went forward and aft on either side. As the rotary drive shaft was turning the geared system, this disc would spin. And when the ball was in the middle, based on the position of the rack, there would be no turning of the latitude or longitude mechanism. However, when the rack was slid either all the way aft or all the way forward, the ball would then be at the edge of the disc, and as the disc would turn, it would activate the longitude or latitude system. Just to summarize again, the controller had two diaphragms which moved in opposite directions based on pitot pressure or pump pressure. As long as the pump was running up against the pitot pressure, it was trying to equalize that and turning the rotary drive shaft, which gave the air position indicator both its mileage information, but also ran the gearing system, which moved these racks fore and aft, and the ball from the center to the outside of the disc to change the latitude and longitude system, and the heading needle, and all of this was driven by rectified signal, which energized this solenoid, which in turn turned the system counterclockwise or clockwise. This later model air position indicator did not use the ratchet and pawl system, but had a reversible DC motor. Here we can see the fluxgate compass system in action, and I have a separate video on YouTube describing in further detail how the fluxgate system worked. But you can see here as the fluxgate transmitter was turned, the repeater and master indicators turned. To simulate the pump and rotary drive shaft, we have a small motor here turning this drive shaft into the rear of the air position indicator. The system was set so that the drive shaft turned 24 revolutions for every mile traveled. So at 80 RPM, that works out to about 200 miles per hour. On the front of the air position indicator, we see a knob to set magnetic variation, the latitude knob, which would set the latitude, and the longitude knob, which would set the longitude. As you can see here, very slowly the mileage indicator is increasing. And you can see here as we move the transmitter, we get a change in heading. With the heading to the west, there would be no change in latitude, and therefore you would see the longitude change, which is down here at the bottom. And it's moving very, very slowly. Likewise, as we turn to a heading of north, you can see that the longitude indicator is no longer changing, but the latitude indicator is changing. The air position indicator could use airspeed and heading to then calculate longitude and latitude. What it could not do is account for wind, and therefore it did not have a ground speed input or a crosswind correction. That had to be figured out by the navigator to find the exact latitude and longitude. This was an early forerunner of the inertial navigation system later used in airliners involving accelerometers and gyroscopes.